Hi, good morning. This is the e-learning lesson video for Honors Math 3 for section 14.4, and this is going to be part 1 of a 3-part series for this particular section. Alright, so for this first example on the note sheet, we have some review problems from the previous lesson, trying to find the limits of these particular functions. And again, these 3 examples kind of go over the 3 different scenarios where we know that for a lot of these limits, limit problems, you could simply plug in the x value or the c value into our function and find the limit. However, for these, when you plug in the 0 into the function becomes undefined. Okay, so again, we're going to review the 3 different approaches depending on the situation. So for the first one, for the tangent, then we're going to let theta, I'm going to do a little substitution, we're going to let theta equal 10x in this expression. And as x approaches 0, we're going to go as theta approaches 0. Okay, so now we're looking at our limit problem as limit as theta approaches 0 of tangent theta over theta, which again we talked about in a previous lesson, that such a limit is equal to 1. Okay, so it's again one of those things where we want to rewrite it in such a way that we understand without having to reinvent the wheel. Tangent theta over the limit as tangent theta over theta is equal to 1. Here again we have a rational function where again plugging in -2 in for x is not going to work for us. So we're going to factor, cancel out the common factors, and then that's going to allow us to use that limit property where we can plug in -2 in for x. So when we do that, we find that our limit for this function as x equals -2 is 5/7. And for this last part of the example 1, okay, so one thing we want to do is going to bring us to a point where we can use a particular property, especially with these straight functions. So I'm going to multiply top and bottom by 3/2. So for the denominator, what that does, when I take 3/2 times 2x, that gives me 3x. In the numerator, I have 3/2 times sine 3x. So now I'm going to take a different view of my limit. And here I have the limit of this function looks like this now. So again, I'm using those properties from the previous lessons. I can split this up as the product of 2 limits. So you can find the limit as x equals to 0 for the constant times the limit as x equals to 0 for this combination of sine 3x over 3x. Because we can use, again, properties, where if you find trying to find a limit of a constant, it's just that constant. Trying to find a limit of x equals to 0 for sine theta over theta, in this case sine 3x over 3x, and we know, again, that's just 1. So the limit for this function as x equals to 0 is 3/2. Alright, now moving on to this next example. So here I have graphed a polynomial function, and on this graph I have highlighted 2 points. This point is at some value c, and here's the ordered pair that goes with that point. And I've also highlighted some random point here, and picking some value x, and here's the ordered pair that goes with that point. Alright, so now what I'm going to do here is I'm going to connect those 2 points with a straight edge to create this line. Okay? Again, this line is called the secant line. Again, a secant line is a line that hits your figure at 2 different points. And with every line, we could always talk about the slope, right? So to find the slope of the secant line, we're going to use our knowledge of the slope formula, right? The difference in the y's over the difference in the x's. So over here, we have the slope of the secant line, right? Difference in the y's over difference in the x's. Okay. Fx minus fc over x minus c. Alright, so now you want to notice that if I were to pick a different x value, say I want to pick one where I am approaching, getting closer and closer to c, right? So if I pick this point right here, okay, so say this is my new x, comma, f of x point. Well, if I connect those 2 points, if I connect that point with my c point, see that, okay, now my secant line, the slope of my secant line is changing. Obviously, right? Again, as I pick different points, right, x points, and I connect them with my c point, right, my slope is going to change. Right? Again, I could pick another one that's closer to c. I can pick this point. Okay, so not to clutter up this graph too much, right, we can see that as I move points, my x points closer and closer to c, the slope is changing. And theoretically, it's going to come to a point that this secant line, as I move closer and closer to c, is eventually going to get to a point where it almost looks like, again, I'm approaching c, I'm not actually going to get on c, but it's going to look much like a line like this, right? Which this is now a tangent line, right? A tangent line is a line that hits your figure at exactly 1 point. Okay, so we are approaching the value of c. What's going to happen as I change my x value, as it gets closer and closer to c, right, that secant line thus changes into what appears to be a tangent line. Okay, so I'm going to highlight a few things here you want to remember going forward as we continue on with this lesson and into the homework. All right, so to find the slope of the tangent line to the graph of y equals f of x to the point c comma f of c. Find the slope of the tangent line. We're going to approach it as a limit. Right? Again, what we're doing here is we are picking points, right? These x points as x approaches closer and closer to c. Right? What is that limit? And so here the limit as x approaches c of the function defined as f of x minus f of c over x minus c. So again, to find the slope of the tangent line, approach it using limits. The limit as x approaches c for f of x minus f of c over x minus c. If the limit exists, the equation of that tangent line, right, is going to be written this way. Right? We're going to be using point slope form to write this equation, where m is the slope, and we're going to use the point c comma f of c. So here we're going to be using point slope form. It's going to be y minus f of c equals slope times x minus c. Okay, so here with this next example, we're going to go ahead and use the above information. So it says find the slope of the tangent line to this function x cubed minus x squared at 1 comma 0. Okay, so here's the graph of that function. Again, when you're graphing this function, we can look for 0, so maybe we can do a little factoring, take out a GCF of x. Now we're left with, GCF of x squared. Okay, cube of x squared. So now I'm left with x squared times x minus 1. So again, we got to find the zeros. Right? What values of x make this function 0? So it's at 0 and at 1. Alright, again, we know this is a polynomial function, so to what end behavior. Okay, so again, things that we talked about before. So here's the graph of that function. Alright, so, and we also want to graph the tangent line, so we're basically trying to look for the equation of the line tangent at 1 comma 0. Okay, so to find that slope, we're going to use this formula. To find the slope of the tangent line, we're going to write it as the limit as x approaches c. So again, our c value in this case is 1. So x approaches 1. And now it's going to be f of x minus f of c up top. So f of x, that's the function. Right, so there's f of x. Minus f of c. So we're going to take this function and we're going to plug in our c value. So we're going to have 1 cubed minus 1 squared, which is 0. So that's where this minus 0 is coming from. Right, so again, from this setup, when I set up, find the slope of the tangent line is we're going to set up a limit. As x approaches c. This is our c value. So x approaches 1. Numerator, f of x. What is the original function? Minus the function evaluated at c. So I plugged 1 in for c. 1 in for x. This is the output. All over x minus c. So x minus 1. Right? 1 is our c value. Right, so simplify this a little bit. So now I have the limit as x approaches 1 of x cubed minus x squared over x minus 1. So here we're finding out the limit of a rational function. Okay, so we're going to do some factoring because I can't just plug in 1 because that will make my function undefined. So the limit as x approaches 1. Do some factoring. These cancel. So now when I plug 1 in for x, I get 1. Okay, so this 1 is the limit of this function, but more importantly for us, this 1 represents the slope of the tangent line. Okay, so at that point, I didn't do that good of a job of graphing this, but here it is. Right, there is the line tangent at this point. So the slope of that line, and what we found out here, is 1. Okay, so we're going to have to continue on with a second video. So go ahead and stop the video at this point and proceed to video number